Hello class, quadratic models and regression. So last unit we talked about quadratic functions, their vertices and their axes of symmetry and their intercepts, etc. And in this unit we will apply that knowledge to certain phenomena that are of interest. So this first question, you want to kick a ball so that it lands 20 yards away from you and so that it reaches a maximum height of 12 feet. Find the function that models the path of the ball. Find where another person should stand so that she catches the ball on the way down at a height of 4 feet. Do this by hand, but use technology to verify your answers. So the first thing I want to observe is that our units are not consistent. Put everything in terms of feet. 20 yards is the same amount as 60 feet. Remember that there are 3 feet per yard. The next thing we want to do is decide on a frame of reference. If we want to model this with a parabola, then we need to have a set of axes in here that we decide where they are. Where do we want the origin to be? Where the ball lands? Do we want the origin to be where the max height is? Do we want the ground to be the x-axis? Or do we want where the ball started to be the origin? Let's go ahead and pick that the origin is where the ball started. We want the ball to land 60 feet away. So we want the ball to hit the ground at the point 60, 0. X will be measured in feet, and our y-axis will also be measured in feet. And we want the height to be at a max height of 12 feet. That's going to be where the vertex is at. The height will be 12, so the second coordinate will be 12, but what about the first coordinate? Well, we're assuming the ball starts at the origin, and by symmetry of parabolas, we know that the vertex has to be halfway between the x-intercepts. So halfway between 0 and 60 feet is 30 feet. So that tells me that the vertex should be at 30, 12. Now we just have to figure out the function that models this parabolic path. Well, because I know the vertex, the way I'm going to go is the standard form. Let's say h of x. X is the horizontal distance the ball has traveled, and h of x will be the vertical distance at that moment x. The standard form of a quadratic function is some coefficient times x minus h squared, and then plus k. So since we know the vertex, we can say that a times x minus 30 squared and then plus 12. Now all we have to do is figure out what a is. And I can do it by using the information I know about this point or this point. It really doesn't matter. If we plug in 60 for x, we expect to get 0 back for y. And if you want to go with non-function notation, you could just say that this is y equals y equals. We know that y will be 0 at the same time that x will be 60. And then this gives me an equation I can use to solve for a. So I'm going to subtract the 12 over. 60 minus 30 is 30, and 30 squared is 900. And divide both sides by 900 to get a, so negative 12 over 900, and that simplifies to negative 1 over 75. So our function, h of x, is equal to negative 1 over 75 times x minus 30, and that's being squared, and then plus 12. So we've done our first set of instructions right there. We found the function that models the path of the ball. Now we want to find where another person should stand so that he or she catches the ball on the way down at a height of 4 feet. This is the point of catching. The ball is on the way down. We don't know where the person should stand. That'd be the x-coordinate, but we do know that we want the ball to have a height of 4 feet. Okay, the way to do this is to change the height to 4, or the y-coordinate to 4, and then solve this equation for x. I'm going to subtract the 12 from both sides, so we get negative 8. I'm going to multiply both sides by negative 75, so 600 is equal to x minus 30 squared. Now we want to square root both sides. We get x minus 30 equals plus or minus the square root of 600. And 600 could be written as 100 times 6, and 100, you can take the square root of it. So 10 rad 6. Or you can just say square root of 600. And then finally add, so we get 30 plus or minus 10 rad 6. There's going to be two different locations where the height is 4. There's going to be a point over here as well. They're going to be centered at 30, and we're going to go 10 rad 6 one way and 10 rad 6 the other way. And that's how you can find out where the two different locations are where the ball will have a height of 4 feet. However, we only want the one on the way down. We want the 30 plus 10 rad 6 is where the person should stand. Person should stand 30 plus 10 rad 6 is about 54.5 feet away from the kicker. Okay, so here is our work for this one here, and we're going to use technology to verify it. Let me reveal the function that we just found, and I'll zoom out. And if you click on the red graph, you'll verify all of these points of interest. So this confirms that we found the right model. We can also use technology to figure out how to answer the other question. I'm going to type in the horizontal line y equals 4, and then figure out where that line intersects the parabola. Now the one we were interested in, of course, was the one on the right, which is at 54.5 roughly. So confirming the work that we did by hand. Let's go to the next one. You throw an object straight up. The height of the object in feet, t seconds after you release it, is determined by the function below. Answer the questions that follow. Do as much work by hand as reasonable, but use technology for tedious calculations and for verifications of your answers. So h of t is equal to negative 16 t squared plus 50t plus 6. Now this is actually a situation where an object is being thrown straight up. It's going to turn around and come straight back down. So this is not like the ball where the ball went off to the side as well. So I'm going to graph this function h of t. I've already typed it in as h of x. Desmos will also recognize using t's as input variables. Anyway, so here we have a function h of t. Let me change the scale so that we can see a little bit better here. Okay, the first thing to comment on is that this particular imagery gives the impression that the object is thrown off to the side, much like the soccer ball was. But in reality, this object was thrown straight upwards. You have to realize that the x-axis, the horizontal axis in this image here, is time. It is not a spatial dimension. It is not a length like it was with the soccer ball. So we're seeing a parabola, a parabolic arch here, but the horizontal is a time dimension. Now, if you click on the screen graph, it'll find all the intercepts and the vertex. It says, do as much work by hand as reasonable. Okay, so how long does it take for the object to hit the ground? To answer that question, you want the height to be 0, and you want to figure out the time where that happens. So that just change this side of the equation to 0 and solve for t. All right, so to do this, we have 0 is equal to negative 16t squared plus 50t plus 6. First thing I notice is that everything here is even, so I could certainly divide everything by 2 to make the numbers a little bit easier. So negative 8t squared plus 25t plus 3. I also don't really love the negative in front, so I'm going to multiply both sides by negative 1 as well. It's going to change all the signs over here, but you don't need to do this if you don't want, but typically I like to have a leading coefficient that's positive when I try factoring. And if you try factoring this, to save time, it won't factor, which doesn't mean we can't get an answer, because we would use the quadratic formula instead. So you would say, okay, well then t is equal to negative b, which is going to be 25, plus or minus the square root of b squared. So 25 times 25 is 625. Keep in mind I'm using this ABC here. So minus 4ac is going to be 4 times 8 is 32, times negative 3 is negative 96, but we're subtracting that, so it'll be plus 96, all over 2a, all over 16. Now I'm just going to go ahead and type this into a calculator. I'm going to do the plus and the minus and get the two different times. Okay, so the first time I'm getting is 3.24 roughly, and this was measured in seconds. And when I do the subtraction, I get roughly negative 0.12. Now the time that we are interested in, of course, is the positive one, the time after we released it. Because we're saying at time 0 is when I released it. Let's do a question 2 next. How high does the object go? Well, this is like finding the vertex of this parabola. And because the parabola is written in general form, and I'm going to use that the t-coordinate is calculated by doing negative b over 2a. I'm looking at this function right here now for my b and a. So we're doing negative 50 over 2 times a. That's going to be over negative 32, which is 25/16 seconds. And 25/16 is 1.5625. 1.5625 seconds is how long it takes for the object to reach maximum height. And then what is that height? Well, we just plug in 1.5625 into our function. And over here, I'm just going to do that. I'm going to insert a new line here and say, okay, what is h of? And then put in this 25/16. And we get an answer of 45.0625. If you want it in fraction form, just hit that symbol there. But let's go with decimal form. 45.0625 measured in feet is the max height. Next question here was, how high is the object after 2 seconds? Right, to answer that question, right, we just have to do h of 2. Just plug a simple 2 into here and do a calculation, but we get 42. It's 42 feet, 2 seconds after release. Okay, now we're going to use the technology to confirm all of this. I already have it graphed here, so I just have to click on the green graph and find all of our points of interest. Now, Desmos is doing some rounding when it gives us these numbers. So the 1.563 was actually 1.5625, and the 45.063 is actually 45.0625. But it's rounding to the nearest thousandth, which is good enough. Also notice that at time 0, the height is 6. This object was thrown upwards, and as soon as it left the hand of the thrower, it was already 6 feet above the ground. And according to this, it hits the ground at 3.241 seconds, which was one of our answers we got by using the quadratic formula. And then the other question was, put a vertical line, x equals 2, and see where it is in our graph. 2 seconds after we released the object was already on its way back down. And it was at height 42 feet 2 seconds after we released it. Okay, now let's move on to the next slide. You can afford 1,200 feet of fencing and you want to build a divided rectangular enclosure against an existing wall as depicted below. Find the dimensions that will enclose the maximum amount of area. Do this by hand, but use technology to verify your answer. Okay, in this situation, if you were to experiment with different ways of using up your fencing, you would see that we get different shaped rectangles and hence different areas. For example, if I put 100 feet for each of these, then how much fencing do I have left over? Well, I have 900 feet still. I could do that for this other side. Remember, I don't need to put anything here. There's already an existing wall. So this accounts for the 1,200 feet of fencing. But the total area of this rectangle right here, and notice it doesn't really matter where the inner divider is. In other words, you can make a smaller section here and a larger section here simply by moving where this middle piece is, and you would still use up 1,200 feet of fencing, and the total area would still be the same. And you would get that total area by doing length times width, and that gives me 90,000 square feet. Well, this is just one way of doing it. The question is, how should I use up my 1,200 feet so that our area is maximum? What if, for example, I use 150 feet on each of these? That means I've used up 450 feet, which means I only have 750 feet left. And in this scenario, when I do the area, it'd be 150 times 750 is 112,500 square feet. So notice this was a better way to do it if I wanted more area. So instead of guessing and checking, we're going to use algebra to find exactly how I should use my 1,200 feet of fencing so that my resulting rectangle has the most area possible. We're going to do it by saying, let's let the widths each be x. Let's introduce a variable, and we'll say the length is y. Okay, we know we have 1,200 feet of fencing to work with. That means that 3x's and add to y, that should add to 1,200. This is called a constraint equation. Whatever x and y are, we want this equation to be true. Now the area of this rectangle is x times y, and we're trying to maximize the area. I'm going to take my constraint and solve it for x or for y. You can choose. It's easier to solve for y because there's no coefficient in front of it, so that's what I'm going to do, but you could also solve this for x. So y is equal to 1,200 minus 3x. And then I'm going to substitute this into the area expression. What this does is it allows me to express area as a function of x. If you were to distribute the x, you get, I'm going to put the x squared term first, so you have negative 3x squared plus 1,200x. Notice it's an upside down quadratic function. It's going to have this shape because the lead coefficient is negative and it's an x squared. And there's going to be x against a when we're done, which means that there's going to be some choice of x I can make that will give you the highest a. We're after the vertex. Find the dimensions that will enclose the maximum amount of area. Do this by hand, but use technology to verify your answer. Okay, a couple things to notice. What's the largest x could possibly be, and what's the smallest it could possibly be? Well, if x is 0, you devote all 1,200 to the y, then you won't have any area. So we're going to say that x has to be in the interval from 0 up to, and what's the largest x could be? Well, knowing that we have 3 x's, and we had 1,200 feet to begin with, 400 feet would be the largest x could be, but it's not a good choice of x because if you use all 1,200 feet of fencing just to do these 3 pieces here, then you have nothing left over to do this piece and you would have 0 area again. Also notice that if you were to find the x-intercepts of this function, set this equal to 0 and solve for x, you would find 0 is one x-intercept and 400 is the other. 0 you get from this factor and 400 you get from this factor by setting it equal to 0. If I were to graph the area function, I can expect x-intercepts at 0 and 400. And I expect an upside down parabola. And we're after the vertex. Well, the easy way to find the vertex of this parabola, because we've already found the x-intercepts, is going to be halfway between the x-intercepts. So halfway between 0 and 400 is 200. And then to find the area, we just have to find a of 200. The other way to get the vertex, of course, is to do the x-coordinate will be negative b over 2a. And you're looking at this version to see what the b and the a are. The c would be 0, but the b is 1,200 and the a is negative 3. So when I do negative b over 2a, double negative 3, I get negative 6, and then do this division, I get 200, which is exactly what we expected to get by using symmetry instead. And then, of course, the y-coordinate would be doing a of 200. I'm going to plug it into this factored version. We get 200 for x, that's the width, times, and then we do 1,200 minus 3 times 200. That's just finding the y, which is the length. So we get 200 times 600, that's 120,000 square feet is the max area. So what's fascinating about this is a problem that has to do with rectangles. When we model its area as a function of x, in this case, we get an area as a inverted quadratic function. Now this said find the dimensions that will enclose the maximum amount of area. So we're going to say that the width, or the x in our picture, has to be 200 feet, and the y in our picture has to be 600 feet. So this really is the answer to this task. These are the dimensions that will enclose the maximum amount of area. So I've typed in the area function, and notice we can't see much on this current zoom. That's because this function goes very high, up to 120,000. I'm going to hide the function and change my y-axis, reveal the function and change my x-axis so we can see the parabola better. And if you click on it, it'll find the vertex for us and it confirms our answer. If you charge $10 for a phone case, you can sell 20 of them in a day. If you charge $8 for a phone case, you can sell 25 in a day. Do steps 1 through 4 by hand, but step 5 can be aided by technology. Find a linear model for the demand as a function of quantity. Now the word demand is simply how much you can sell. It's the relationship, I should say, between how much you can charge and how much you can sell at that price. We need to introduce some letters here. We can say X is quantity and P is price. To do step 1, we want to make a table that relates the data here. We know that when the price was $10, that we could sell 20. When I lowered the price to 8, I could sell 25. And these are phone cases. And this says find a linear model for the demand. We're going to assume that the relationship here is linear, so we have to figure out the slope. So it's going to be the change in x divided by the change in p. Notice I'm treating x as my dependent variable and p as my independent variable. So our slope here is change in x. We do 25 minus 20, that's 5, divided by change in price. 8 minus 10 is negative 2. And the units here would be cases per dollar, suggesting that for every $2 decrease in price, our quantity goes up by 5. Now we want to construct the equation. Now normally our point slope equation looks like this. But you have to be careful. This was assuming that y was the dependent or the output variable and x was the input variable. But now this is a little bit backwards. If I adjust this formula, it would look like this. X minus x1 equals the slope times price minus price 1. And you can use either point here for your p1 and x1. So I'm going to use 1020. So x minus 20 is equal to the slope we found, which is negative 5 halves, times price, p, minus 10. So find a linear model for the demand as a function of quantity. As a function of quantity, we said x was quantity, so we actually want to solve this one for p, for price. But I'm going to begin by distributing the negative 5 halves. Negative 5 halves p, negative 5 halves times negative 10. That's going to be positive, plus 10 divided by 2 is 5, times 5 is 25. If I were to solve for x, this is what this would look like. Add 20 to both sides, we get 45. Now, which question did we answer by doing this? First of all, let's verify this is correct. Plug in a 10 right here for this price. 10 times negative 5 halves is negative 25. Add 45 to that, you get 20. Check. Plug in 8 to see if it works. 5 halves of 8. Do 8 divided by 2 is 4, times negative 5 is negative 20. And then add that to 45 is 25. Check. So this is the correct linear relationship between x and p. But currently, it is x written as a function of p. P is price. So we actually answered question 3 first. We found a linear model for the demand as a function of price. If I want to go back and answer part 1, then I just got to take this equation and solve it for price. So we have x minus 45 is equal to negative 5 halves p. Now multiply both sides by negative 2/5. And so we get price is equal to, I do want to be clear what I'm doing here, I'm just multiply both sides by negative 2/5, and I'm distributing. And negative 2/5 times negative 45 is positive. A fifth of 45 is 9, and double that's 18. This answers question 1. Here's our demand as a function of quantity. Item 2, find a model for the revenue as a function of quantity. Now revenue is price times quantity. And so if we want to do revenue as a function of quantity, then I want only x's over here, no p's. So I would do a substitution. I would use this and change the price to negative 2/5 of x plus 18, and then multiply that by the x. This is revenue as a function of x. You could distribute the x if you want, or you could leave it factored out. And this answers question 2. Question 4, find a model for the revenue as a function of price. So now I want to start with the same starting point. Revenue is price times quantity, but this time I want only P's on this side. So I want revenue to be a function of price. So I'm going to use what I found in step 3 and replace the X with that expression. And so this answers question 4. It's revenue as a function of price. And you could distribute the P or you can leave it factored out. If you distribute it, you'll see that you have a quadratic that's upside down. Same thing would be true for step 2. If you distribute the X through there, you'll see you have a quadratic. You'll see X squared with a negative leading coefficient. So upside down parabola. Now, question 5 we can do with technology. Revenue is a function of X is this one here I'm calling R1. Change our scale so we can see what's going on here. Notice our maximum revenue occurs when X is 22.5 and we have 2 intercepts. Okay, now this is a function of X. X was quantity. Let's do a vertical line in here. Let X be 30. So if you want to sell 30 phones, then you're going to have to charge a certain amount. And that amount is dictated by equation 1. You would simply plug 30 in here for X and see what the price would be. Negative 2/5 of 30, a fifth of 30 is 6. Multiply by negative 2 is negative 12. Add to 18 is $6. So if you want to sell 30 phones, you need to charge $6. And if you do 30 phones times $6, you're going to get $180 in revenue. That's what the y-coordinate of this revenue function is telling us. The only 2 bits of data that are apparent here, all the points on this orange graph, are x-coordinates, which is quantity, number of phones you want to sell, phone cases I should be saying, and the revenue you'll make selling those phone cases. It doesn't tell you the price. We haven't graphed that relationship. This is R against X. The vertex, if you do 22.5 phone cases, then your revenue will be $202.50. So the max revenue will be $202.50. An obvious question is, well, what was the price then? Well, if you take this 22.5 and plug it in right here, you'll get that price. Or we could do the following. I'm going to graph now the R as a function of price, which I have here. It's the next orange graph. Notice it's a different looking parabola. This is R against P. The horizontal axis is P, which is price, and the vertical axis is R, which is revenue. What's not obvious in this graph is what the correct quantity should be. But it's saying that if you charge $9 per phone case, then your revenue will be a maximum of $202.50. Charge $9 per case. And you would get this 9, if you knew the X had to be 22.5, plug it in here and do this calculation, you should get price is $9. If you know the price is $9, you plug that in here, charging $9, you can sell 22.5 phones. And so then when you multiply these 2 amounts, you will get the maximum revenue. Looking at this image here, this intercept, 18, 0, what is this telling us? It's saying that if you try to charge $18 per phone case, you would get 0 revenue. And the reason is because our linear model predicts that when you try to charge that much, you can sell no phones. So your revenue will be 0. Okay, let's move on to the next task. An apartment complex has 105 units. If rent is $300 per month, then all units will be occupied. For every $20 increase in rent, 1 less unit will be occupied. Do the following. Find a model for the monthly revenue as a function of the number of times that rent was increased by $20. We're going to make a table and see if we can make sense of what's going on here. And let's say what the rent is and then what the number of units. So X is the number of times we increase by $20. So if X is 0, it means we haven't increased rent. So we're keeping it at $300, which means the number of units will be 105 units. Let's see what our revenue would be though. So I'm going to add an extra column here for revenue. You just multiply 300 and 105. So $31,500 would be our revenue if we don't increase rent. But if I increase rent at the expense of losing units, let's see what happens. When X is 1, this means rent has gone up by $20 and units have gone down by 1. And when I do 320 times 104, my revenue climbed to $33,280. What if X is 2? So we're going to increase by $20 twice. So this will be now $340 per month per unit. But we lose another unit in the process. But when I do 340 times 103 units, my revenue is still gone up. It's now $35,020. So the question is, will this continue to happen? Well, eventually no, because even if this gets extremely high, eventually we're going to get down to no units filled. So your revenue will be 0. So even though revenue is currently increasing, I expect it to drop back down to 0 at some point, suggesting that there might be a maximum. And our goal is to figure out what that maximum is. So if I leave x, let's come up with a formula. The rent should be 300 plus 20x. Right, this is how we were getting each new rent, where x is the number of increases. The units goes down by x, and the revenue will be the product of these two things. So revenue as a function of x is equal to 300 plus 20x, and then 105 minus x. I could FOIL this, but I'm not going to. If I do FOIL this, though, you will notice that we're going to wind up with a negative 20x squared term and then some other stuff. This will be a quadratic function with a negative leading coefficient, so it'll be opening downwards, so suggesting that we will have a maximum. But we've actually done part 1. Now we're going to do part 2 with technology. Find the rent that will maximize the monthly revenue and give the maximum monthly revenue. If you were doing this next part by hand, you could find the two x-intercepts and then find the vertex by averaging their x-intercepts. Or you could expand this into general form and do the negative b over 2a to find the vertex. All right, so here's my revenue function, 300 plus 20x times 105 minus x. And I'm going to change my y scale until I can see the entire thing. I wanted to click on the blue graph so I can highlight these intercepts and vertex. Okay, notice the y-intercept, 0, 31,500. This is saying that if you do 0 increases in rent, then your revenue will be 31,500, corresponding to this first row. When x is 0, which means no increases in rent, revenue is 31,500. Look at the x-intercept down on the bottom right, 105, 0. That's saying that if you do 105 rent increases, you expect a revenue of 0, because the number of units will have shrunk to 0 at that point, so we're going to get 0 revenue. But we're after the maximum revenue, and that occurs when x is 45 and the revenue is 72,000. So a little image, this is r against x. The maximum of this was at x equals 45 and revenue was 72,000. All right, so find the rent that will maximize the monthly revenue. So we know that x has to be 45. That means 45 increases by $20. So the rent will be the 300 base plus $20 times 45 increases. So the rent should be $1,200 per month. If you charge $1,200 per month, you will lose 45 units, which means you'll only have 60 units, and the max revenue is going to be $72,000 per month. And we have one more slide here. We're going to do quadratic regression. Each night for 6 days, a runner slept various amounts of time. Following each night, the runner ran the 100-yard dash and recorded her time. Use technology to perform quadratic regression. Quadratic regression is finding a parabola that best fits data versus linear regression, which is finding a line that best fits data. So do quadratic regression and then use this model to predict the number of hours she should sleep to maximize her performance. All right, so when she slept 8.4 hours, she was able to run the 100-yard dash in 12.9 seconds, etc. As expected, if she slept too little, she took longer to run the dash. Also, it looks like if she slept too much, almost 10 hours, also her times suffered. So we're going to treat the hours of sleep as an x-coordinate and the time that she ran the 100-yard dash as the y-coordinate. You can see that the data does look parabolic. Sometimes data is not obvious whether you should do a line to try to model it, whether you should do a parabola to try to model it, but it does sort of have a parabolic look to it. So let's try a parabolic regression. So I've already entered the data into this table here, and the headers are x1 and y1. The line of best fit would be y1 tilde m times x1 plus b. Use y1 and x1 because those are the headers of your table. We've already talked about how to do linear regression, but what's new to this unit is quadratic regression. What you type in is what you see down here, y1 tilde ax1 squared plus bx1 plus c. The tilde is what tells Desmos that you want to do regression. And then it gives you what the a, b, and c are so that we have a parabola of best fit. We do wind up getting some sort of parabola like this. Maybe this isn't the best drawing of what we just saw, but good enough. And we're after the vertex of this parabola. We call the data x1, y1. So we typed into Desmos this expression. So A is about 0.355, B is about negative 5.649, and C was about 35.675. You just got to click on the parabola, and Desmos will automatically find its vertex right there. And the vertex is 7.961, and the second coordinate was 13.187. So this suggests that she should sleep 7.961 hours, and that the time on the 100-yard dash will be expected to be 13.187 seconds. Now you might say, well, she actually did better when she slept 8.4 hours, but that might have been a fluke. If we gathered more data, we might see that on average that these figures here are better. And this is just a model. No model is exact, but some models are useful. And that wraps up the lecture on this unit.